Alright, in this video we're going to look at measuring predictive accuracy, and these are some common things that are used in order to report how well a model is actually working or not. It's very important when you do these, what you're going to look at is the validation period. So even though you train it on the training period, then we're going to actually use the validation or this test period in order to report our final accuracy measures, and particularly when we compare it between one version of the model and another version. So the forecast error we can just represent as an actual minus predicted error. We've looked at this guy before, but we have some different ways to express that. So one would just be the mean absolute error. It's also called the mean absolute deviation. The deviation is just the error, and MAE or MAD, and that just means that we just find the average of all of these errors, and we look at those in absolute value. So we make sure that we're not including the positive and negative errors like the over-under fitting in this. An average or mean forecast error. In this case, we actually keep the sign so that we can tell if it's under or over forecast. So if we have a positive or negative number, that's going to give us some additional information. The MAPE is a very common one because it is scale independent. So this allows us to compare performance across multiple data sets that might have different scales. And so in this case what we're doing is we're looking at the errors relative to the actual value itself, which helps to scale it down. We're going to divide it by the total number, and then we multiply by 100 because it's typically reported instead of as a percent, actually as a whole number. The root mean squared error is just going to be all of our errors squared divided by n, and we take the square root, and that's kind of like a standard deviation or a standard error. This measure will have the same units as the data series, so that again kind of gives you a little bit of information, but it's not as good for comparing across data sets. Another thing I'm sticking in here, this isn't in the text, is about the tracking signal. This is used to look at forecasting models along the way to sort of track if things are starting to get out of hand, if things are predicting either too high or too low. So what we can do is actually create the tracking signal by looking at the sum of all of the errors up to a certain point, as well as the mean absolute deviation up to a certain point, which would be like a certain place that we are actually forecasting. And then it's kind of like measuring out about 3 standard deviations, which translates into greater than 4 or less than 4. In some books you might see this as 3.75. And this allows us to actually come up with the actual tracking signal. I've summarized, this is a screenshot out of the book that shows how to calculate some of these different calculations. It doesn't have the tracking signal on it, and we'll actually go through an example together that includes all of these. One other thing that is added, there's another measure called the MASE, the mean absolute scaled error. And this is good whenever we have zero counts in our data, because of the fact the way that the MAPE, it's like a really strongly used one because it's scale independent. Everybody likes it. Since if you have data that actually has zero counts, what will happen is that you'll end up with zeros in the denominator, and that will cause this not to be defined anymore. So what we do is we look at a instead of the actual value in the denominator, we look at the training mean absolute error of the naive forecast. So it's kind of interesting. It actually kind of gives us a benchmark based on what the naive would be doing in order to figure out how well it works. So again, we'll play with these in an example so you can see how all these are calculated. One thing to look at is that sometimes forecasting errors are more serious if they are over or underfitting, depending, or that has a focus on our profitability. So if it's more costly for us to overfit something, then we need to be really aware of that, or if it's more costly to underfit it. And I actually put a reference here of an entire paper that talks about that in the Journal of Applied Forecasting. So it's kind of an interesting thing to look at, trying to figure out what's going on with our over and our underfitting, depending on how this forecast is actually going to be used. Two other final comments. Forecasting errors are not normally distributed, so we can't really deal with them a lot of times like the way that we might with like a regression error. So a lot of times what we'll do is we plot them so that we can see where we have some extreme values. So things that are really way far off, either high or low, show that we have some kind of problem. And so a lot of times we'll just create a distribution, or again some kind of a plot, which would be a distribution of that. And then we can also create prediction intervals. So a lot of times we don't just want to forecast a single value. We would much more strongly like to have something like a measure of risk attached to that. So we could create like a 95% prediction interval by using the percentiles of the forecast errors. So again, we don't have our normal distribution that we might in some of your previous stat classes have used in order to get the prediction or confidence intervals. So instead what we'll just use is the actual percentile. So we can just break up our errors, and then we can kind of have a range of how often or how big or small we expect those errors to be, and then we can just put that around our actual forecasting point, and that will allow us to create our prediction interval.